So, welcome back. I am going to start off from where Jailal left off, and so this is the title of my session, and I am Venkatesh Raman from Institute of Mathematical Sciences. This P versus NP question has, it's one of the fundamental open problems of this century, and it has engaged computer scientists for the last 40 years since this Cook-Levin theorem. And so, on the one hand, complexity theorists have been, trying to identify properties of problems rather than one problem at a time. So, you want complexity classes defined under different measures and trying to see whether they collapse or are they different, right. That is the question about P versus NP. Is P equal to NP or are they different, right. So, what I am going to cover in this next 1 hour is some algorithmic developments in the last 40-50 years in trying to deal with the fact that there are lots of problems which are NP complete. Okay. So, when Cook-Levin proved in 1971 that Jailal mentioned click, actually they showed this satisfiability problem, and in 1972 Richard Karp added about a dozen problems which are NP complete by doing these reductions from one. So to show some problem is NP complete, you want to show that every problem in NP reduces to that problem, right. That is the hard work of the first paper. But once you have proved some problem is NP complete, you can start from there and reduce to your favorite problem to show this problem is NP complete. And this is what Karp did, and he added a dozen problems NP complete, and soon the whole industry opened, and now there are thousands of problems which are NP complete. Okay. So, what do we do with them, right? So, because these are practical problems, because people have encountered them, that is why they tried hard to design efficient algorithms and they tried to show it is NP complete. And so, showing NP complete or NP hard is sort of an evidence that we do not expect a polynomial time algorithm, because if you have a polynomial time algorithm for the problem, it collapses P and NP, the conjecture is settled. So, it is widely believed that showing a problem as NP hard is an evidence that there is no efficient algorithm for it. By efficient, I mean an algorithm which is running in polynomial in the input size. But the problem does not go away, you need to solve it somehow. So, what do we do with it? Okay. So, that is the topic of this session. So, let me start with our understanding of what does it mean by a problem pi is NP hard. So, I am going to be talking about optimization problems, okay, not really decision problems, there is no yes or no questions, optimization problems. So, for some technical reason they are NP hard, but it does not matter, every NP problem reduces to that. A problem is NP hard means that there is no algorithm that runs in time polynomial in the input size and answers and gives exact optimum solution for all input instances. Right? Well, not quite. This if P were equal to NP, which we do not know, then this statement is not true. Right? This is what is widely believed. So, I am going to say that this is a conjecture. Right? So, this is not a fact, but this is more of a conjecture. That let us take our favorite problem, vertex cover. Right? You have a graph and you want to find out, let us say, the minimum vertex cover in the graph. For that optimization problem, because testing whether there is a vertex cover of size k itself is NP hard, you do not expect an algorithm that will run in time polynomial in input size and gives exact optimum solution for every graph on n vertices. Because if you do have such an algorithm, then that would imply that p is equal to n p and we would have solved the conjecture, but that is not what people believe, right. So, now the vertex cover problem does not go away. People do want to solve, because these problems are modeled from the important real life problems. So, think of, you want to place some ice creams or petrol bunks on vertices, so that at the end of every road, at least at one end of every road, you have a petrol bunk. Okay. You can come up with fire station, whatever, come up with various examples where these problems are modeling real life problems. So, you need to find minimum sized this parameter in your graph and you need to solve them somehow. But we have this bad news that the problem is NP hard. So, you do not expect this to happen. So, what do we do with it, right? So, we ask, what can you relax here? Okay, you can't solve it in polynomial in input size, but how much more you need, right? Okay, you can't give me the exact minimum solution, but can you give me something close to the minimum efficiently? Well, you can't solve it for all input instances, but can you solve it for a large class of input instances? Okay. So, these define relaxation of each of this define a different paradigm in dealing with NP complete problems. Okay. So, for example, so how much more than polynomial? Right? Do you really need exponential time, or do you need 2 power n time, or do you need what? Is it enough to do it in 1.5 power n, or is it enough to do in 2 power square root of n time? These are all super polynomial, but I live with the fact that I do not expect a polynomial time algorithm, but how much can you do, right? This is a topic of there are books on this topic, exact exponential time algorithms. There are algorithmic techniques known, where you can just do something much better than just doing brute force. Okay. Suppose I do not want the exact optimum, but I want something close to optimum. How close to optimum can I get in polynomial time? This is a topic of approximation algorithms. Right, these are well developed areas in the last 40 years of algorithm design. I do not want to solve it for some all inputs, but maybe I want it for some special inputs, right. So, for example, polynomial is something I want to relax, exact is something I want to relax, and for all inputs is something I am trying to relax now. So, instead of all inputs, I want to solve it for some special inputs, right. So there is a whole industry of special classes of graphs, for which some of these hard problems can be solved efficiently. And then there is another area which is fairly recent, that is parameterized complexity. So, it is somewhat I would say it is a combination of. So, on the one hand, for general instance I want an exact exponential algorithm. I am worrying about exact optimum, not approximate, but my input is not very special, but maybe a little bit more than special. Okay. So, for special inputs I have very efficient algorithm, for general input I have exponential algorithm. Can I sort of smoothen things in between and capture that by some parameter, right. So, parameterize either the input or output and design algorithms that are only exponential in the parameter. meaning that your input comes with some parameter. This parameter may be how far it is from a special input, right. If it is really special input, I have a polynomial time algorithm. The farther I go from the special input, the algorithm will be exponential in this parameter, but it's polynomial in the rest of it. So when I reach the most general input, it will be exponential.
That is, if the parameter is fixed, it will be polynomial fixed parameter.
Yes, but that is, suppose the parameter is k. Okay, there are two interpretations of what you just said. So if k is fixed, there are two kinds of algorithms. There is an n power k algorithm, that is also polynomial, but there is a 2 power k times n square algorithm, that is also polynomial, but these are different kinds of polynomials, right. So that is why I have said exponential only in the parameter, but on the input it is sort of polynomial independent of the parameter. Okay, so what kind of problems have this kind of behavior? So what I am going to do is use one running example of the vertex cover problem you have seen and illustrate all these paradigms in this 1 hour. Okay, so that is the goal. Okay, good. So you all know what the vertex cover problem is. Your input is graph G, and there are two versions. The most optimization version would be find the minimum vertex cover. Well, what is a vertex cover? It is a subset of vertices such that for every edge, one of the endpoints is in my solution, right. This is the formal definition of a vertex cover. It is a subset of vertices such that if you give me any edge, at least one of the endpoints is in this subset. So the decision version would be is there a vertex cover of size k? Okay, so the input may have a k. So let us look at an example. You have seen so give me the smallest vertex cover for this graph. Okay. Somebody said 1375. Okay. 136. I don't know. I am just writing down whatever you are saying. So is 1357 a vertex cover? Let us just check. It is not. Why is it not a vertex cover? Because the edge 4, 6 is not covered. So I may need to add something more. Let us say. Is 4257 a vertex cover? Because 3, 6 edge is not covered. 1367. 4256 might work. Okay, you don't need 7. Okay, you can see that even for such a small graph, it is not so easy to figure out what is the minimum vertex cover. Okay, so no wonder the problem, well, not quite, but anyway. Okay, so is 1367 a minimum vertex cover? Is that a vertex cover first? Yes. Somebody said no. What is not covered? It is covered. So 1367 is a vertex cover of size 4. Is there a vertex cover of size 3 here? 4 to 6. 4 to 7. 4 to 7 does not cover the edge 1 5. How do I show? I mean, so how do I show that there is no vertex cover of size 3? If you don't choose 4, you have to. Oh, good. These are excellent observations which I am going to use later. Anyway, if you don't choose 4, you will pick 1 3 6. Yeah. Then you have to pick one of 5 and 7. So you have 4 vertices. But if you choose 4, if you choose 4, there is 2 3.
Then if you choose 6, 3 6 then if you don't choose 6, then you have to choose 3 5 and 7. Otherwise you will have to choose 6 also.
So here is my argument. So if you don't choose 4, then you need 1 3 6 and you still have 5 7 edge to be covered. So you need 5 or 7, right? If you choose 4, then here is my argument, because we are going to use this. So here is a matching 1 2 3 6 and 5 7. What does that mean? That we need to, you need to pick at least one from each of the matching edges, so you need 3. So if you don't choose 4, you have some other argument to show 4 is necessary. If you choose 4, then even after choosing 4, I have this matching of 1 2 3 6 and 5 7. So you need at least one from each of the matching edges, so you need 4. Okay, good. So now you understand what vertex cover is, how difficult it is, and so on. Let's first think of a brute force exact algorithm to find the minimum vertex cover. What will you do? Okay, finding min vertex cover, right? For every subset of V, check whether S covers all edges. Right? How do you check whether S covers all edges? Run through all edges, check their endpoints and see if they intersect S, right? So what would be the running time of this whole algorithm? For that particular step, O(n) square or O(m), if m is a number of edges, and for the first step, you're going to run it over all possible subsets. So it's 2 power n times m, right? M is a number of edges in the graph, right? And then you pick the one which is the minimum size which covers all edges, and that's your minimum vertex cover. So here is one brute force exact exponential algorithm which takes 2 power n times m, and then this is sort of our benchmark algorithm. We will later improve this algorithm. Okay. So we'll come back to this. Now I mentioned something about matching, right? Can you find a maximum matching in a graph efficiently? You have seen that, right? There are number of algorithms. So suppose M is a maximum matching. This is going to be a very useful thing which we can do it in polynomial time, right? Of size m, that is number of edges in M is small m.
Can we do this in polynomial time in least one by partition?
Yes. You may or may not have seen it, but yes, you can do it. Yeah, it's more involved. For bipartite graphs, it's easy. You can use some flows, but for non-bipartite graphs, you can find it. It's a quite involved algorithm. It's one of the classical algorithms due to Edmonds. So now what can you say about the size of minimum vertex cover? Greater than or equal to maximum matching. Did you see that? Because we saw that in that example, it's greater than or equal to m. This is a very useful thing to know, right? Because these edges are disjoint, that's what matching means, and a vertex of this, and you need at least one from each of these edges, and a vertex from this edge will not cover any other edge in the matching. So, you need a private vertex for each edge in the matching. So, it's at least m. Good. So, now are there examples where the minimum vertex cover is strictly more than m? Can you, let's go back to our example. What is the maximum matching in this graph? Sorry? There is a node which is connected to everything. Okay. So, what is the maximum matching size in this graph? 3, right? So, 1, 2, 3, 6, 5, 7 would be a maximum matching. 2, 3, 1, 4, 5, 6 would be a maximum matching. So, maximum matching size is 3, but the vertex, we argued the minimum vertex cover size is actually strictly more than 3. At least there are examples where this is the case. So, now there was a famous theorem due to Koenig, and it was independently proved by Egervary in 1931, that in bipartite graphs, maximum matching size and the minimum vertex cover size are the same. Have you seen that in your course? Okay, good. So, in bipartite graphs, the size of the maximum matching is equal to the size of the minimum vertex cover. In fact, this proof of this theorem is also algorithmic. I mean, there are proofs which are algorithmic. You can find the maximum matching and then do a little more work and get your minimum vertex cover. Okay. So, what does this tell you? That you can actually solve minimum vertex cover in polynomial time in bipartite graphs. This was one of the things I wanted, right? That, oh, you can't solve it in polynomial time for all input instances, but can you give me some special class of instances where you can solve in polynomial time? Yes, you can solve minimum vertex cover in so the proof can be converted into an algorithm. Polynomial time algorithm to show that vertex cover is actually in P for bipartite graphs. Actually, we will actually see a special case of bipartite graphs where we will run through the algorithm, but this is one of the paradigms I was mentioning, that you want to know what is the a largest class of graphs where you can actually solve it in polynomial time. Okay. So, in fact, it turns out this was probed by Grotschel, Shriver and Loash. This required 82, where you can say vertex cover is in P in a much larger class of graphs called perfect graphs. Okay. I do not know, you may or may not have seen perfect graphs. If you have not, do not worry about it, but it is much larger than bipartite graphs. Bipartite graphs sit inside, they are all perfect graphs. Okay. Okay. Perfect graphs are graphs where for every induced subgraph, the size of the maximum click and the minimum coloring number are same. Chromatic number, right? Okay. If you know these things, fine, otherwise do not worry, but all I want to say is that here is this one paradigm to deal with NP hardness, is that, oh, okay, in general it is very hard, I can't solve it in polynomial time, but can I exploit some structure in my input and design a polynomial time algorithm? Yes, if your graph is bipartite graphs or perfect graph. So, let us actually design an algorithm, because this is another idea. So, one idea you have seen is that vertex cover size is at least the size of the matching, right. I am going to use another idea where we will design a nice polynomial time algorithm for a special class. Let us say, okay, or you have a general graph. Suppose you have vertex with degree 0. What can you say about it? So, you have an isolated vertex in the graph. You are trying to find a minimum vertex cover in the graph, but here is a vertex which is not connected to any edge. What can you do?
It won't take it anymore.
It's not in the vertex cover.
So, what can you do?
It won't be in any code.
Right. So, you can just throw it away from the graph. You can simplify your instance. This is a very polynomial time step, right. Just find the isolated vertices, throw them away, right. So, delete them. If your graph has isolated vertices, delete them. But suppose x is a vertex with degree 1, what can you say?
It has to be chosen or the edge from which it is going.
Yeah, so suppose it is like this.
Either V has to be chosen or X.
Okay. Can you say something better? Yeah, you could just choose V, right?
It's like an exclusive OR. It cannot be both X and V. That's not necessary.
You cannot have both x and v, because if you choose both x and v, what is the role of x? You can throw it away, right. Can you not always choose v? Okay, I'm glad it is not obvious, because it's important. So sometimes, so you're trying to be somewhat greedy here. Greedy may not always work. So one needs to be very careful. So what I'm going to argue is that, yeah.
There is a vertex cover with X and not V, then we can take out with X and put V.
Exactly. Excellent. So here is a proof, right? Suppose there is a minimum, we are not talking about any vertex cover, we are interested in minimum vertex cover. Suppose a minimum vertex cover contains, so we already argued that it does not contain both x and v. Right? If it contains x and v, I can throw away x has no rule. Suppose it contains x, but it does not contain v, right? So I just put v and remove x. The size of the vertex cover has not changed, and it's still a vertex cover. So there is always a minimum vertex cover that contains v, right. So without loss of generality, whenever I have a degree 1 vertex, I can just throw its neighbor, pick its neighbor into the solution and throw it away, throw both of them have done their job, right. These are some simple pre-processing steps you can do. These are all polynomial time. Remember, we are fighting against exponential algorithms. So n square, we are not that bothered about it in this big scheme of things. So, pick x's neighbor in the solution. So, x's neighbor here is v, and delete x and v. Why can I delete x and v? Because I picked v has covered all the edges incident on v. So now focus your energy on finding the minimum vertex cover on the remaining graph, and you can always add v to it, and that's the minimum vertex cover in the whole graph, right. Nice. So these are some pre-processing rules you can always do. Good. So now suppose your graph is a tree. Can you find the minimum vertex cover in polynomial time?
It's a bipartite graph.
Great. Tree is a bipartite graph, so you can apply that big theorem and solve it. But I am just giving you a much simpler algorithm, right? What is a simpler algorithm? So somehow root the tree and do something. But no. Let's see. Suppose I do this pre-processing. Suppose I do this pre-processing, right? I just argued that if I want to find a minimum vertex cover, you can delete degree 0 vertices, and if you have a degree 1 vertex, you just go and pick its neighbor and delete both of them. Keep doing it, right? I can. There's nothing that stops me from not doing this again and again as long as it's possible, right? Suppose I do it on a tree, what happens?
And no point in a tree, there is no leaf.
Yeah,
Yeah.
always a leaf in a tree.
Good. So, this is a property of a tree, there is always a leaf. In fact, there are at least 2 leaves, right, if the tree has more than one node. There are always 2 leaves. So, you can find a neighbor of a leaf, include it in the solution, delete it, find a neighbor, find a leaf, find its neighbor, include it, keep doing it, the whole tree will vanish and you have gotten your minimum solution. It is a very simple, you can implement it in linear time, n square time or something like that. It's not very hard. That there is a very simple polynomial time algorithm to find a minimum vertex cover in a tree. We already know that since tree is bipartite due to Koenig's theorem, you can find in polynomial time, but here is a simple algorithm. Okay. So, this is the game in this, right. So, keep applying degree 1 pre-processing step. And you will be done. Okay. So, we can solve minimum vertex cover in trees, in bipartite graphs, in perfect graphs and all that, right. Some I have told you, some I have not. Perfect graph is quite sophisticated algorithm. So, now let us come back to the exact exponential algorithm. What is the first exact exponential algorithm we designed? 2 power n times m, right. So, let us try and improve that. Okay. I want to do some slight improvement to that. So, the point is, what did we do there? We tried all possible subsets. Clearly, some of the subsets are redundant, right. If we can find that quickly and prune them down, then you can improve your running time, right. So, here is a another observation. In fact, you observed it when we were doing this example, right. If you do not choose 4, you have to pick 1, 3, 6, right. This was a very nice observation. If you do not pick a vertex, then you have to pick all its neighbors, right, in any solution, because if you do not, we saw it in the example, if I do not pick 4, then who is going to cover this edge 1, 4? Must be 1. Who is going to cover this edge 4, 3? It is 3. So, if you do not, so let us capture that observation and see how we can use it in an algorithm. So, let me make this observation. If a vertex x is not in the solution, for me the solution means minimum vertex cover, then all neighbors of x must be there. So, I am going to try both these choices. Okay. So, what do? I go to my graph. First of all, remember there are no isolated vertices. So, every vertex is some edge. So, I go to one vertex and say, hey, you may be in the optimum solution. I am going to try that. What does it mean by try that? I am going to delete it and find the minimum vertex cover in the remaining graph. And I get some number. And in the other branch of my recursive algorithm, I am not going to include that vertex. Then I have to include all its neighbors and then go in the remaining thing and find a minimum vertex cover. Now, let us see how much time will this take, right. So, here is a branching algorithm using this.
If we input all the neighbors, we can delete those neighbors.
Exactly, but let us see what happens, right. So, here you have G and you want to find minimum vertex cover. So, I am going to say, so here is my min vertex cover of G. I am going to write a very simple recursive thing and let us figure this out. So, min vertex cover, minimum of min vertex cover of G minus x plus 1. That means, I pick x into my solution, find the minimum vertex cover of the remaining graph and add it to it. That is one possibility. Or I am not including x. So, what do? I am going to G minus neighbors of x plus degree of x, right. because if I don't include x, I am going to pick all its neighbors, that is degree of x, and I am going to delete, in fact,
Neighbor of x minus x.
minus 1, right, because
You also did
Minus x. So minus x.
yeah.
So with the step above it, why don't we do g minus x minus neighbors of x? Because we don't.
Because here we are including x.
Yeah, but like the bracketing is wrong. You should know. Bracket.
No, the bracket should be above.
Correct?
And last bracket should be there.
So this must be like, yeah, okay. Okay, so now, so this is sort of a recursive algorithm, right? In one branch, I am deleting one vertex, right? I am picking one, and in one branch I am deleting one vertex. In the other branch, what is the minimum I might delete?
It's at least 2.
Yeah, if x is degree 1,
Oh, you already did it.
if x is degree 1, then what have I done? I would have even pre-processed it. So I wouldn't even come there. So let's say make minimum degree 2 by pre-processing.
So the pre-processing is actually same as this.
No.
At least you always delete at least 3 words.
Exactly. So first thing what I do, I delete isolated vertices. When I have a degree 1 vertex, I pick its neighbor, delete them, and so on. I've done all that. At the end of these pre-processing steps, as long as it's not possible, what I have is a graph with minimum degree at least 2, maybe even more if I am lucky. So in this branch, I am throwing away one vertex. So I have, it's a recursive algorithm. So if I start with n vertices here it will be n minus 1 at most. Well, it's clear exactly n minus 1. Here it's at most. At 1 I am throwing here and 2 I am throwing here, so it's at most n minus 3, right. And what do I do in each branch? I continue to do the same thing. I'll pick a vertex, not branch, I include it in the solution, or delete all its neighbors in the other branch, and I continue. So what sort of the running time do you think you will get?
Sort of like Fibonacci recurrence.
Good. If I put n minus 2 here, it's exactly Fibonacci, right. T of n is T of n minus 1 plus T of n minus 2. What is the solution to Fibonacci recurrence? 1.618, right, asymptotically 1.618, but this is even better because it's not even n minus 2, it's n minus 3, right. Even if I don't do the isolated degree 1 pre-processing, then it will be like Fibonacci. So I am going to now write this as this is much better than 1.618 power n times whatever polynomial time you are trying to do to include your solution, delete the vertices and so on. So I am going to say some m or something. Okay, it's much better. It's if you actually solve the recurrence, it's 1.5 something because of the n minus 3. Okay, so we've improved from 2 power n.
We could also select the x with the highest degree.
You could take x with the highest degree, but in the worst case, maybe the highest degree is 2. That's a good. Let's get to that, right? So now you get the game. You are playing in this exact algorithm, right? So let's just come back here. So what he says is pick a vertex with highest degree, because then the drop here will be much larger. But when will it be larger? So suppose we assumed here that minimum the degree is 2. That's what n of x is 2 and x is 1, so that is 3. But what if you are unlucky and every vertex is degree? We already ensured there is no 0 or 1 vertex. So it's a 2 regular graph. How does a 2 regular graph look like? It is a cycle. It's a collection of cycles where you can solve vertex cover easily. Good. So let's get that out of the way. So it's one more pre-processing, right? So if no degree 3 vertex, solve in poly time. So this all adds to this poly time here. So at the end of it, now if when I branch here, n of x is at least 3 and this is 1. So it becomes n minus 4. So it's even much better. It's like 1.5 4 something, I forget, you can check. Good. So, this is the game in exact exponential time algorithm, where we live with the fact that it is NP hard. So, you do not expect polynomial time algorithm if I really want to solve it for every instance of the problem, but can you at least improve the base of the exponent. And it is in fact interesting that there are some problems for which you can actually do with even 2 power square root of n time. Okay. So, for example, problems in planar graphs and things like that. Okay. So, what have I told you? I have told you about the game in special instances, right. You want to solve in polynomial time and pick a large class of inputs for which you can do it, like perfect graph. You want to solve exactly, you are living with general instance, then at least try and improve the base, and here is the game, you can do it, right. Now, I want to just touch upon 2 more things, which is the parameterized complexity. Suppose my G is very close to a tree. Okay. If it is a tree, we know how to solve it in polynomial time, right. Just the degree 1 rule itself will take care of it. Suppose G is a tree plus some k vertices, right. So, somebody has given me, so my real instance has some k vertices, there may be a lot of edges here, I do not know, but if you delete these k, so again there may be a lot of edges of this type. If you delete this thing, then let us even say not a tree, but maybe a forest, right. It makes it even more general. Because the tree algorithm will work for forest also, we can just apply it on the same connected component. So, then what you have is suppose a tree like this, right. If you delete these k vertices, what you get is a forest.
Each possible combination of the k vertices, each subset of the k vertices.
Okay, let us try. What do we do? So, now we want to solve, okay, can we hope to solve it in polynomial time? Polynomial in n and k?
No, every graph is forest plus k vertices.
Does everyone see that? Because you can take, I mean, you take any graph, delete everything except some 2 vertices. The 2 vertices is a forest, because there will be at most an edge or 2 independent points, right. So, every graph is a forest plus some n minus 2 vertices, right. So, if I am able to solve it in polynomial in n and k, then I would have solved the vertex cover from every instance. So, I do not expect a polynomial in n and k for this. So, I have to live with exponential in k, and we were trying to see what sort of an exponential in k we want to deal with. So, his suggestion is, so let us say I am going to call this an S, which is the modulator. So, here is an algorithm, right. For every subset S prime of S. So, what is this S prime in your mind? It is a subset of k vertices, yeah, but which is part of my solution. I am looking for a minimum vertex cover in this, right. So, what is my goal? I have this graph which is close to a tree, right, in the following sense that there are these k vertices, if you remove the graph becomes a tree or a forest. So, what he is saying is, okay, I am trying to find a minimum vertex cover, the minimum vertex cover will intersect my S in some subset, should it? If it does not, it is an empty subset, fine. So, I am going to try all possible subsets including empty subset. I am going to say that S prime is my intersection of S with my optimum solution I am looking for. I am going to try all possible S primes anyway. So, once I fix S prime, so what does it mean? Let us say this is my S, this is my S prime. I have decided that I am going to pick this set of vertices into my solution. What can you say now? Can you have edges here?
No.
Why not? Who is going to cover those edges? If if I have an edge like this, only one of these points can cover, but I have already made my choice of my intersection of my minimum vertex cover into S, right. If there is an edge here, then this choice is wrong, move on to your next choice, right. So, until I get a choice of S prime where this is independent, right. So, S prime has no edges, sorry, S minus S prime has no edges. Okay. Now, what are the vertices to be covered now? What are the edges to be covered? Anything incident on S prime has already been covered because I chose S prime. What are the other edges to be covered? So, anything inside,
Like anything from S prime to the 3, so there would some edges from S prime to the 3 that I need to cover.
But S prime is already covered.
S prime is covering. So, any edge inside the forest I need to cover, I will come back to it later. What are the other edges? The edges from S minus S prime to these guys. Who is going to cover them? So, if you have an edge like this, who will cover?
One of these.
No, but S, but that
That particular vertex, you are forced. You are forced. There is nothing else, no other choice. Once I made a choice that this is my intersection with S, then for any other edge, the other endpoint is forced into my solution, right. I am trying to extend my S prime solution to a minimum vertex cover. There are some choices are forced, right. So, for every subset S prime contained in S, include neighbors of vertices in S minus S prime. So, if you have a vertices in S minus S prime, neighbors of S minus S prime in V minus S. So, this is V minus S. So, in V minus S, if you have some neighbors of S minus S prime, those edges the only way you can cover is by picking the other endpoint, because I have somehow made a choice that these vertex is not going to be picked. So, I am going to pick all those choices, these edges. Now, what is left is to find the minimum vertex cover in the remaining graph. What is the remaining graph?
Collection of trees.
It is a collection of trees, it is a forest where I know how to find minimum in polynomial time, right. And add a minimum vertex cover of the remaining forest. Keep doing this for every subset S prime and keep track of your number and pick the one which is the smallest, and that is your minimum vertex cover, right. Because this is exactly a minimum vertex cover will look like. It will intersect S with some subset, and then it has to be a minimum vertex cover, and then the remaining the endpoints are all forced, and then it will be a remaining minimum vertex cover for the remaining forest. So, forest I know how to, I can find it in polynomial time. So, you can do this. So, how much time have you spent? 2 to the k into some poly in.
By the way, I think there's a difference between tree. It could be generalized to bipartite graph or anything.
Very nice. That is the next step I was going to say. Where did we use the fact that this is a forest? Where did we use?
When we ran the algorithm.
That you can find the minimum vertex cover of a forest in polynomial time. So, instead of a forest, you throw in any graph where you can find a minimum vertex cover in polynomial time. Let us say bipartite graph or perfect graphs. Then if your graph is just k away from that, then this would give you a 2 power k. So, it is interesting that this exponent is k, not n. Okay. So, that means that it is very smooth growth of the running time. As the graph becomes more general and general, then it is 2 power n, but for graphs which are close to whatever you can solve in polynomial time, this method gives you a 2 power k times polynomial in m. So, in general this is what parameterized complexity is. So, your input has, let us say a graph, but it could be anything, but there is a parameter, and the goal is design algorithm with runtime some f of k times poly in C, where this C is independent of k. So, this is like an n square. So, you are mentioning about for a fixed k it is polynomial time, even if it is n power k I would call it a fixed k, it is polynomial time, but here I want on the. So, that means wherever the parameter is small, you have a very feasible running time algorithm, but it does not say anything about the fact that in general the problem is NP hard. We have not designed a polynomial time algorithm because there will be an exponential part on this parameter k. Okay. So, let us ask following question. The input is now what is this parameter k? It could be anything that makes sense. That is the beauty of this area, right. So, in the previous example I used k as the parameter which is sort of its distance to a tree, a distance to a forest. But suppose I change k as and ask the following question: does G have a vertex cover of size k, size at most k? Right. I give you a graph on n vertices and I ask, is there a vertex cover of size at most k? How much time do you need? What would be sort of a brute force algorithm? Right. I am not asking for a minimum vertex cover. My question is there, so I have a budget. This graph I am allowed to cover with some 30 vertices or something. Can you do it is my question.
N choose k or something?
N choose k is one brute force algorithm. Notice that that does not fit into this running time which I am after, because I want this C to be independent of k.
But by the way, C would also be independent of n, right? So C is just a constant.
C is a constant, yes, of course C is a constant, but I just want to emphasize the fact that it is independent of k. So, for this vertex cover problem you can try all possible subsets of size k and then check whether it is a vertex cover by running through all edges. So, that is like an n choose k algorithm, but can you think of a better algorithm? We already saw some branching in the general paradigm, right. Can you use some branching to design a better FPT fixed so this is called fixed parameter retractable, okay, that is a technical term here.
If you can choose, like, if you can find, if you decide one vertex is in the vertex cover, it reduces to a problem for size k minus 1.
Exactly. If I do not pick it, k minus its neighborhood. So, it is exactly like the exact exponential algorithm we chose, but what is the difference here? There it was like 2 power n kind of thing.
Here the size k is at 6.
So how far? So, the depth of your tree, you do not go on, right. So,
That is the tree is fixed by k also.
correct. So, what is the thing? So, the branching algorithm is your G and k. I am going to look at G minus x, k minus 1, because x is into the solution. See whether there is a vertex cover of size k minus 1 here. In the other branch, I am going to pick G and n minus x and look for a vertex cover of size k minus the degree of x, right. What is the height of this tree?
K minus the degree of x minus 1. X is also different.
Yes, but what is the solution size, right, because k is my solution size. How many did I pick into the solution? Yeah, so here, okay, fine, you want to say there.
Yeah, that one also is minus.
No, there it is not. I want to make a difference, because here, yes, x is deleted and all its neighbors are deleted, but all its neighbors are the ones which are included into my solution. I am looking for a solution of size k, so I just have to subtract only the degree. So, what, can you just give me a rough bound on the depth of this tree? K, because this is the difference between the exact exponential algorithm, right. There I was looking for a minimum vertex cover. Here once I go down and then I reach, suppose I have some G prime and I want to know, is there a vertex cover of size 0? Which graphs have vertex cover of size 0? If the no edges, edgeless graph. If it is edgeless, then I will say yes, otherwise no, and abandon the branch and move on. If there is an edge here, that means this branch did not succeed in getting me a vertex cover of size k, right. So, this would give me the Fibonacci or whatever, but not power n, but power k, because the depth is, because the solution size is the parameter here. Okay. So, I have covered special inputs, I have covered exact exponential algorithm, I have talked about parameterized complexity, where the goal is to design algorithms of running time like this. In fact, there is a complexity hierarchy, there are some hardness theorem which tells you that there are some problems where you do not expect such an algorithm and so on. So, let me just spend 5 minutes maximum on this last paradigm, which is another important paradigm, which is approximation algorithms. Right. So, I want to find a minimum vertex cover which we know is NP hard, and so I don't expect a polynomial time, but I want something close to the minimum vertex cover. So, what is the natural heuristic?
Pick the edge with maximum degree.
Keep a vertex with the maximum degree, right? So, greedy would be keep picking vertices with degree, with highest degree, with the delete the vertex and all the edges incident, and in the remaining keep finding a vertex with the highest degree and keep doing it, and you get a solution. Will it be a vertex cover to start with? Yes, because if there are still some edges left, you will go and pick a highest degree. So, this set of vertices will cover all the edges. Clearly, it is a vertex cover. But how is it close to the minimum vertex cover? We have solved it, and this is a polynomial time algorithm. So, clearly, you do not expect it to give me an optimum vertex cover for all instance, because if you do, then you have proved P equal to NP and
By the way, so it's the highest degree in the graph.
in the remaining graph, So, the exercises, I do not have time. So, find examples where this is not optimum. This is easy to come up with. What is more challenging is how bad is it, right? With respect to optimum, how bad is it? And this is usually very hard because we do not even know what the optimum is, because we do not know how to find the optimum. So, the challenge in approximation algorithms is not so much the running time, which we will usually make sure that it is polynomial time, but the solution produced, how good is it to the optimum solution. Okay? This is usually hard. So, it turns out this algorithm, the size of the solution produced, the size of the greedy is at most some log n times optimum. Okay, this is a bit involved, and there are examples where the greedy will actually produce as large, the ratio between the greedy solution, the optimum is as large. Is less than or equal to? Yeah, because I have multiplied by it.
Sir, this can be proved.
This can be proved, yes. This is a theorem I wrote. That this, so there are two things I am saying. One, this algorithm is pretty good approximation in the sense that it is never, it will definitely produce non-optimal solutions at several instances, but it is never more than log n times the optimum. Okay. So, if the optimum is 20, this may produce 100, okay, 5 times for a large graph. Okay. So, one can prove this, and there are examples where this is as bad as this, but I am going to give you a very simple algorithm. So, this is called the approximation ratio. So, the challenge in approximation algorithms is to improve this approximation ratio, come up with algorithms where the approximation ratio is as close to 1 as possible, right. So, I mean in polynomial time, okay, I can't get optimum, but can I get 1 plus epsilon times optimum, and there are examples, problems where such algorithms are possible. But for vertex cover, I am going to conclude by giving you a very simple approximation algorithm with ratio 2. Yeah.
So this log means ratio.
I think it is natural log. So, this E, but for now I am just going to put a big O there and let you check this out, but I think it is natural log. So, here is a very simple algorithm, okay, approximation algorithm for minimum vertex cover. Find a maximum matching. M, pick both endpoints of all edges of M. Let us call that as S. Output S.
This is just the set of vertices.
So how does, so let's see, the graph will look like this. I find a maximum, okay, then we'll quickly see that you don't even need a maximum matching, a maximal matching is enough. Maximal matching is even much simpler to find. So suppose this is a maximal matching, okay. The graph may actually have a lot more vertices, right, but there are no edges among them because this is a maximal matching. So how are the other edges? It's like this. So the graph looks like this, but this is my, there could be edges like this. So this is my graph, this is my maximum matching, and all I am saying is pick this set of vertices. This is what I call it as S. First, is it clear that S is a vertex cover?
Yeah.
Why?
Because every edge
If there is
has
a
one
edge which is not covered, then it would be
Exactly. If S is not covering some edge, that means what? That edge is sitting outside. Why did you not include it in your maximal matching? Your matching, so remember this uses only the fact that it is a maximal matching. Since it is a maximal matching, there are no other edges outside. So S covers everything clearly. So S is a vertex cover. Now I want to argue is S is never more than 2 times the optimum. Is that obvious? Because remember, very early on we said minimum vertex cover size is at least size of a maximum matching. We saw that, right? But how much have I picked? But size of S is simply 2 times. So this is, yeah, I mean, so from here it should be clear that cardinality of S is at most 2 times min vertex cover.
So S should be less than or equal to 2 times.
Opt.
No, I'm talking about that 2.
Hmm?
As that is a maximum matching, S should be less than or equal to 2 times.
S is equal to, because what did I do? S is exactly both endpoints of all edges of matching.
Yeah.
So cardinality of S is equal to 2 times the size of the matching.
Yeah, but N is not the maximum matching.
Oh, okay, fine. Sorry. Yeah, okay, good. So then you need one more inequality. But bottom line is that whatever I have picked, so one line argument is I need at least one endpoint of each of the matching edges. I picked 2. So I am at most 2 times the optimum. Okay. So this is sort of counterintuitive, right? Because the greedy you expect is a very natural thing, that I am picking a vertex which covers all edges. But somehow here I am saying take an edge and pick both its endpoints. To cover that edge, one is enough, but the other endpoint is to cover a lot of other edges, and that gives you a 2 approximation algorithm. And what we know in the last 30 odd years is that this approximation 2 has not been improved. It is a famous open problem to improve the approximation ratio of vertex cover from 2 to even 2 minus epsilon or something. Okay. So this is the game in approximation algorithms where you want something close to the, so there are problems where you can get 1 plus epsilon close to the optimum. There are problems where you can show that under some assumptions you can't do better than log n ratio and so on and so forth. Yeah.
So this, having an approximation ratio of 1 plus epsilon is get arbitrarily close.
Yes, exactly. So where do you pay for it?
You pay for it from constant factor.
In the running time. In the running time. So if you have 1 plus epsilon approximation, the algorithm will be like n power 1 by epsilon or something. So if epsilon gets closer and closer, you will get very high running time.
So it will be like n raised, 2 raised to 1 minus epsilon and then some polynomial kind of.
2 raised to 1 minus, yeah.
Times some polynomial kind of.
It's even worse than that, not even 2 raised to 1 minus epsilon. It's 1 by epsilon or n power, things like that. I think I'll stop.